Uh, we started. Hello, students. I hope I'm audible and my screen is visible also. I we started the call instruction in the last class, but the thing is that we would like to finish loop instruction first, and then we will go to the call procedures, etc. Right? Okay. So, what is a loop instruction? Okay, we have seen conditional jump instructions. Okay, so loop is one form of a branching instruction. You can say that program control instruction, but the thing is that it will also include the functionality of checking CX, that is a count, and auto decrement inbuilt. That means what will loop do? It will jump to a specified label or a specified location if Cx is not equal to 0 after auto decrementation of Cx. Okay, so it will jump to a specified label or a location if Cx is not equal to 0 after auto decrementation of Cx. So where it will be used is it will be used to repeat a series of instructions for some number of times. Okay, what will be that number of times it will be repeated? That number of times will be present in Cx. Okay, so number of times the sequence is to be repeated is loaded into Cx, not Cl, Cx. Okay, so each time the loop executes, Cx automatically it will decrement by 1. Okay, if Cx is not equal to 0, then execution will jump to at the destination specified by the label. Okay, for example, if I have say loop x1, let us say that. Okay, if I have loop x1 here, okay, it will loop to this location x1. Okay, as long as Cx doesn't become 0. Okay, Cx will be decremented every time it encounters this loop, and it will jump to this Cx jump to this x1. Okay, every time until Cx becomes 0. Right? So loop x1 is the label here. Okay, so Cx, if not equal to 0, it will jump to the destination specified by the label in the instruction. If Cx equal to 0 after the auto decrementation, that means first you will jump to first you will decrement it, and then you will do you will check whether if it is 0. If it is not 0, then you will jump to the specified destination. Okay, now the destination address is of type short address. Okay, now what do you mean by short address? We'll see subsequently. Basically it will be a very short jump that you have. That means the number of locations that it will jump or it will go is lesser than 128 steps or 128 bytes. The address that you will specify by that label. Okay, the either basically whenever what happens when you actually let us go to the example here. Whenever I specify loop x1, okay, now as we have seen in the conditional jumps, okay, we have seen one example, if you remember, in a previous class, where the label will be replaced by the displacement. The label will be replaced by the displacement. So in this loop, it will be a short jump. That means it will be the displacement will be of 8 bits only. Okay, it will be the displacement will be 8 bits only. We'll see more about this short jumps, near jump, far jumps, short jump in subsequent classes. But for now, we can understand that loop is actually a short jump only. Okay. So loop affects no flags. That is the important thing. It will not affect any flag. Okay. Right. So let us take one example. Okay. So you want to add a data in one block of memory with data with another block of memory. Okay. You want to add them, and you want to use it using loop. Okay, so the size of the block is 100 words. Okay, so that is what we want to do. So how do you do that? So I have block one, which is 100, 100. Let us say I just put it as 100 loop 01. Okay. So what will 100 loop 01 do? What will 100 loop 01 do? Anybody? Unmute yourself and tell. Latika Agarwal, would you like to answer? Because I have only 67 students, so I have a privilege of asking anybody and ask. If at all you don't know, it's not an issue. What does 100 loop 01 do, Latika? Any idea? Madhav Gupta, what does 100 loop 01 do? Okay, Latika, you have unmuted yourself. Yeah. Don't worry, even if it is wrong, no issues at all. I'm sorry, I cannot hear you, Latika. Okay, right. I already have some answers. So it will put 01 or 100 loop 01. It will to put 100 loop 01, 01 100 times. But please remember they are word locations. So each location will be 0001. It's a word. Okay. So 0001. It will be repeated 100 times. Okay. Similarly, I have block 2 where I will have 100 loop 02, and then count I will have DW as 100. Okay. The reason why I'm putting count as DW, not DB, is you will be knowing. See, first I have cleared the direction flag and move CX comma count. Okay. See, now I said move CX comma count. If count was actually a byte, if count would have been a byte, then I will have an issue here. I can't move it into CX directly. I have to move into CL and CH. I have to make 0 and so on. Okay, to avoid all these things, have uh, declared count as DW. So move CX count, move SI offset block 1, DI block 2 offset, and then load SW. What does load SW do? What does load SW do? Anybody would like to answer? Can raise hand. Anybody who would like to answer, please raise your hand. Right, Mitesh, Madan.
Sir, it will load a string of size word.
It will load a string. Sorry, it will load.
It will load a string of size word to register AX.
You won't say load a string. You would say load a word into AX, right? From SI pointer. Okay, pointed by SI, right?
Okay, fine.
Right,
Yes,
Mitesh.
sir.
Yeah,
Yes, sir.
it will be pointed by SI. Okay, so basically one word of data from block 1 will be now loaded into AX. Okay, and then what I will say, add AX comma ES colon DI brackets. Okay, now this is not so much essential. This overriding is not so much essential here because you are using model tiny only here. However, it is okay. It's like you can say safe side. Okay, so you have add AX ES DI, and then you say stos W. What does stos W do? What does stos W do? Again, anybody would like to raise a, yeah, just Tushar.
Stores that word into AX.
No, 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 not stores.
Sir,
Yeah.
it moves the data of the AX register
Mm.
to the ESDI and increments the DI.
Right, right, exactly. So it stores AX into stores W will store AX into, because it's a word, stores W is a word. So AX will be moved into the location pointed by DI in the extra segment, and DI will be incremented. Now, when I say loop X1, what will happen is it will go to X1 after CX is decremented. CX will first be decremented. If it is non-zero, then it will go to X1. Okay, so the whole process, that is this particular counting, or sorry, adding, will continue until CX becomes 0, right? And every time it loops, it will decrement CX. Okay.
Excuse me, sir.
Yes.
So do we need a CLD command when we already have the loop auto decrement?
No, not required. Not required. Here, loop will always do a decrementation only. Yeah, you don't require that. Yeah, no, you require that. Okay, you require this. Anybody who would like to tell why we are specifically putting
So
CLD?
because of the storage B and loadage B to work increment the
Increment
uh,
mode. It is
yes.
basically for the load SD and load SW and stars W. For that particular thing, we are actually clearing the direction flag. It's not for the loop. Loop will always do a decrementation only, right? Okay. So just like you have in sorry, conditional jumps, you have conditional loops also. Okay, so loop E or loop Z, both are same, so they will loop while equal. Okay, so how does they work? So they will loop while CX is not equal to 0 and the 0 flag is equal to 1. Okay, loop E or loop Z, they will loop. Okay, or it will go to the destination address repeatedly until CX is 0 and CX is not 0, or until CX is 0 and until ZF is not equal to 1, or as long as CX is not equal to 0 and ZF is equal to 1, it will keep looping. Okay, so each time you loop, CX will be decremented. Okay, if CX is not equal to 0 and ZF is equal to 1, execution will jump to the destination which is specified by that particular label. If CX is equal to 0 after auto decrementation, or ZF is equal to 0, either of the condition is happening, it will not jump to the destination address, but it will go to the next sequential instruction after loopy. Okay, destination address is a short jump. Again, here also, that means the destination address must be within minus 128 to plus 127 bytes. Okay, 8 bits will be used for specifying that offset. So because it's a signed number, 8-bit signed number, so therefore you have minus 128 bytes to 127 bytes. So that is a short jump. Okay. Okay, let's take an example here. So I have BX offset. So I decremented BX. CX will be 100. Okay. I incremented BX here. Okay. So first of all, I have pointed it to the first location of array, decremented and then incremented. So it will again come back to the first location of the array. Okay. Now I am comparing BX with 0FF. Okay. I'm comparing BX with 0FF. If at all, if it is equal, it will go to this particular location. Okay. Loop while equal. If at all it is unequal, it will go to the next instruction. Let us say that I have an instruction here after loop E. Okay, I have an instruction after loop E. Okay, something like say add AX comma DX, let us say that, or say something like that, or BH. No, you can't have BH, CX, or just have DX. Okay. Okay, so if at all they are not equal, either if 0 flag is equal to 0 is not equal to 0, or CX equal to 0, then it will come to this particular location, right? Okay, so see, it exits from the loop when CX is equal to 0 uh, uh, when it will actually exit from zero, exit from the loop, either Cx is equal to zero or the zero flag is not equal to one. Okay, that is also possible. Okay, these are different conditions. So one possibility is that Cx becomes zero. Okay, then also it will come out of the loop. Okay, Cx is equal to 0 and zero flag is still 1. In that case, all the elements in the particular array are FFH. Okay, and if Cx not equal to 0, then what happens is Bx will actually point to the first element which is not FFH. Okay, if it comes out of the loop with Cx not equal to 0, that means what? That means zero flag has become 0. Okay, zero flag becoming 0 means what? That means it has encountered some byte. We are looking at byte or word. We have to actually specify actually byte pointer. This is a okay. We are specifying it 0ff. So it will point to a byte which is not equal to 0ff. Okay. If Cx equal to 0 and zero flag equal to 0, the last element was not FFH. Okay. The last element was not FFH. So that is the exit conditions. What is the interpretation of this? Right? Similarly, just like you have loop E, you have loop NE also, loop NE or loop NZ. Okay. So what this will do is it will loop while Cx is not equal to 0 and zero flag is equal to 0. Okay. While it will loop while Cx not equal to 0 and zero flag equal to 0. Okay. So let us say the same example that you compare with 0dh instead of 0ff. Okay. So if you compare it and you put a loop ne here, so it will loop as long as you don't have it will loop as long as you do not find 0d and as long as Cx is not equal to 0. Okay. If on the exit of the loop, again similar different conditions that you have, let us say that on exit the Cx is equal to 0 and 0f zf is equal to 0. Okay, Cx is equal to 0 and zf equal to 0. Okay, that means that 0d was not found in that particular array. Okay, it is looping as long as it is not equal. That means it has come out of the loop with Cx is equal to 0 and zf is equal to 0. That means what? It has traversed to the whole array and it has also not found 0dh. That is why zf is equal to 0. Okay, if Cx equal to 0, that means Bx will now point to, it has found 0dh. Okay, it has found 0dh. That means Bx points to the first element where which contains 0dh. Okay, if Cx equal to 0 and zf equal to 1, okay, in that case the last element was the one which is last element of the array is 0dh. Okay, right. So this was all about loop instruction. Now let us go back to the compare sorry, not compare, the call instruction that we was looking at. But before that, if you have any queries, please let me know. Any queries? Sure, Pursat.
So yeah, I had a doubt in the loop instruction. So when I mean the decrementation of Cx is implicit in the loop instruction. So doesn't the decrementation affect the zero flag?
No, it doesn't affect.
So,
It doesn't affect.
thank you, sir.
Okay. Any other queries? Okay. I hope you were clear with the imal and mul instruction that we were looking last class. Is that clear? Mul and imal that we were looking, mul and imal and div and idiv that we were looking last class. Anybody have any query with that particular thing?
Sir,
Yes.
sir, if there is IDIV, then and the dividend, like if it's dx colon ax divided by some 16-bit word, then
Mhm.
and the dx colon ax was a negative word, then the remainder would be negative or positive.
Okay, 1 second. Let's look at that particular thing. Entire screen. Okay, right. You are talking about div or idiv? Sorry, imal or
idiv
idiv?
idiv.
Okay, so we are looking at idiv. So let's look at here. So in idiv, as we know, we will either do this is a sign division. We will divide a word by a byte or a double word by a word. Okay. So when we are doing a word by, I'll come to your question, Tushar. If when you are dividing word by a byte, so what will happen is the dividend will be in AX, okay, and divisor that you have is a byte which is specified either by register or a memory location, okay, and after the division is done, the AL will have the quotient and AH will have the remainder, okay. Now in this case, to divide a byte by byte, okay, we put the dividend byte in AL and fill AH with the sign bit of AL. Okay, that is one way we actually do it. Okay, so similarly, if you do the double word by word, so double word will be specified by DXAX, and the divisor will be present in the either the register or memory location which is specified by this instruction. Okay, the consequence is the AX will have the quotient and DX will have the remainder, okay, and no flags will be affected, and the sign of the remainder will be same as the dividend. Okay, sign of the remainder will be same as the dividend. Yeah. Okay. Can you repeat your question, Tushar?
Sir, so yeah, I was saying this only, that if the dividend is negative, then we would leave remainder as a negative thing. So whatever
Yes.
is the least negative, we will leave
Yes.
that.
Yes. Yes. Yes.
Okay, okay, sir.
Right. Right. Similarly, in IML, okay, same thing you will do. This is a sign multiplication. Okay. So you will do in IML, it will be source times AL if it is a byte multiplication, and it will be source times AX if it is a word multiplication. Okay. And the source, as we have, the source can be a register or a memory location, and the result of a byte multiplication will be stored in AX. If you are doing a byte multiplication, byte with a byte, that is AL with a byte. If you are multiplying AX with a word, then the result of the word multiplication will be present in DXAX. Okay, it will be present in DXAX. Okay, and carry flag and overflow flag will be 0 if the MSB or MSW, whichever is the case, if it is byte or word multiplication, is 0. The MSB or MSW word is my most significant word is 0, then this will be 0. So this will allow the users to detect whether detect and perhaps discard the unnecessary leading zeros. Okay, that will be helpful. If MSB and MSW contain some part of the result, then CF and the carry flag and the overflow flag will be 1. If it has some, non-zero part, MSB or MSW, then this will be 1. Okay, right. So I hope mul and imul, div and idiv are also clear, right? Okay. So let's continue with the call instruction. Okay, so we looked at the call instruction, or we started the call instruction. Now, what does call instruction do? Call instruction, as I was specifying yesterday. Okay, so whenever you give a call instruction, what will happen is the program control will jump from the main program to a sub program. Okay, the sub program will be specified. I mean, the call instruction will specify where it has to jump. Okay, and the sub program will be executed, and then at the end of the sub program you will have a RET instruction. When you say RET instruction, it will come back to the main procedure and it will start executing from the next instruction after call. Okay, next instruction after the call will start executing when it comes back to the mainline program. Okay, now there can be two types of calls. One is called as a near call and another is called as a far call. Okay, so what do you mean by a near call? Near call means the current IP will be saved. Okay, so let us say that I have a call. Let us say that call. Okay, let me see if I have an example. Some label. Let us say some call, some x1. Let us say that, and you have some add instruction after call. Okay, add ax comma bx. Let us say that, and your IP value, that is your the offset value here is 0012h. Okay, this is the IP cs colon IP. Okay, so therefore when call is being executed, the value of IP is 0012. Okay, so now when it encounters call x1, and if this call instruction is actually, or this particular call is actually a near call, okay, then only the IP will be saved into the stack. Okay, IP in this case is 0012, that will be stored into the stack. Why? Because after the subroutine is executed, it will start executing this particular instruction. So I should know where I should actually come back. So therefore the IP value will be stored. So this is called as an near call because you are jumping within the segment. Okay, near call means you are jumping, or the procedure, the subroutine. Okay, subroutine is within the segment. Within the same segment. When I'm saying same segment, I'm referring to the CS, the code segment. Okay. On the other hand, if it is a far call, okay, both CS and IP, they will be saved into the stack. Why? Because when you do a far call, both the CS and IP value will be changing. It will go to and this is also called as inter-segment call. Okay, because you will jump to another segment, a different segment. Okay, so because of a far call, both the CS as well as IP, or both of them will change, and therefore before jumping to, or before going to the subroutine, I will store both CS and IP values into the stack. Okay, CS and IP values into the stack. Okay, and as I told, in the subroutine, the last instruction that you will have is RET. Because you will have RET instruction, when you have this RET instruction, it will retrieve the next instruction after call. In this case, if it is add AX comma BX, it will retrieve its call. Okay, and it will retrieve the next instruction's address and put back into IP, or IP and CS in IP and CS in the case of a far call. Okay, it will restore basically, and this is in the case of a near call. Right? Is it clear? So when you have a call instruction, it will jump to a near location. If it is a near call, it will jump to a location within the same segment of CS. It will jump to a different segment if it is in the case of a far call. In the case of a near call, what I will do is I will store the IP values into the stack. Okay. In the case of a far call, I will store IP and CS into the stack. Okay. And when RET instruction is encountered within the subroutine, it will retrieve the next address in the case after the call instruction. Okay. The next instruction, the next address that is to be retrieved will depend on whether it is a near call or a far call. If it is a near call, I will just retrieve the IP value from the stack. Okay. In the case of a far call, I will retrieve the IP as well as CS value from the stack, and it will be loaded into the IP and CS registers. Right? Okay, clear? Any doubts? Any doubts? Right. Okay. So now the near calls. Okay, near calls can be of two types. Okay, one is the direct within the segment call, which is or indirect within the segment call. Okay, the within the same segment only, the jump location or where I have the subroutine can be specified by a label. When I say call label, some label L1, L2, some label. Okay, so what will happen is this label will have actually the relative displacement. Okay, it will have the relative displacement. That displacement will be added to the IP value. Okay, and this is a signed displacement. Okay, it is a signed displacement. So when I say call, let us say some label L1. Now L1 is some location within the segment, somewhere over here, within the same segment. Okay, I have some set of instructions at location L1. Now L1, when you are assembling the program, L1 will be replaced by the displacement value, just like we have seen in the case of that jump instruction. If you remember, the displacement was, we calculated the displacement and replaced that label with that displacement, right? You remember that example? So in the same way, L1 will be replaced by the displacement. So therefore, the next IP value, okay, the IP will be pointing to here. Instruction pointer will be pointing to the next instruction. Let us say I have add AX comma B. Sorry, I have add AX comma BX. Let us say that. So IP value will be actually specifying or will be pointing to this particular location. So IP will be added with the D16. Okay, the displacement, which is specified by this label, and it is a sign displacement. That means it can either go backwards or can jump forward also. Okay, so that is how we have the relative displacement. This is called as a direct within the segment call. Why it is called direct? Because the displacement we specified within the instruction itself. On the other hand, I can have the indirect within the segment near call. What do you mean by that? Suppose let us say I have call BP. Okay. Now what will happen is BP register will specify the new IP value. So whatever is the value which is present in this particular register will be directly moved into the IP. There is no addition that is done here. No addition is done here. You will just put BP value into the IP instruction pointer, in this case BP or whichever register you specify. Okay, that register's value will be copied into the instruction pointer and it will jump to that particular location. Okay, right? On the other hand, I can also have some memory location giving the IP value. Okay, so I say call word ptr bx brackets. Okay, if I say this thing, then the location bx, okay, will give you the IP value. Let us say that DS value is say 2000. BX value, let us say, is 1000 H. Okay, so it will go to a location 2000 colon 1000 H. Okay, which is nothing but 21,000 H. It will go to that particular location. Let us say that particular location had 0, 0 and pre-0. Okay, 21,000 is 0, 0, 21,001 is 30. And therefore now IP value will become how much? 0030. Am I right? Am I correct? Am I correct
So
or not?
it will be 3000.
Yes, it will be 3000. Why? Because again, Little Endian thumb rule is lower address will always have the lower byte. Lower address will always have the lower byte. In this case, 21,000 H has 00, therefore it will have lower byte. Okay, 21,001 is a higher address and therefore it will have a higher byte. Okay, so IP value, new IP value will be 3000H. So it will go to that particular location within that particular segment and execute that procedure which is starting from this particular address. Okay, so this is called as an indirect within the segment call. Why? Because it's like just like you have a register indirect addressing mode. Okay, indirectly you are specifying the IP location. Okay, on the other hand, you can have a far call. Okay, you can have a far call. Okay, for example, if you have inter-segment far call where both the CS and IP will be changed. Okay, so you can specify it this way: call IP low, IPH, CS low, and CSH. Okay, you can specify the direct jumping address within the instruction only. Okay, call IP low, IPH, CS low, CSH. Okay, you can specify the whole address here itself. Okay, so there IP low, IPH, the instruction pointer will change to this particular address, and the code segment will change to this particular address. So this is called as a direct inter-segment far call. Okay, you can have an indirect inter-segment far call by specifying it in the form of some register location, or sorry, memory location. For example, call d word double word pointer bx brackets. Okay, when you specify this, the first word will give you the IP value, the second word will give you the CS value. Okay, second word will give you the CS value. Okay, so in this case it will be so let us say that you have a location, or you have DS value as, again, let us say 2000H. BX value will, let us say, is 1000H. Okay, so it will go to a location which is 21,000H. Okay, so let us say this is 21,000H. Okay, and let us say it has 0030 0040. Okay, let us say these are the address. So these two locations will go to the instruction pointer, and these two will go to the code segment. Okay, so the new code segment will be equal to 4000H, and new IP will be 3000H. And so it will jump to a location which is 4000:3000H, which is nothing but 43,000H. It will jump to this particular location, and it will start executing the instructions from this particular location. Okay, so this is called as a indirect inter-segment far call. Okay, it's called as an indirect inter-segment far call, right? Okay, and direct inter-segment far call will be specified by IP low, IPH, CS low, and CSH. Right? Okay. Any queries? Any queries? Can you give an example? Yes, we'll take an example of a direct inter-segment. Yes, we'll do that. 1 second, please. One second. I'm actually looking for a particular example here. Okay, apart from that, are there any other queries? If you want, you can unmute yourself. Apart from there, are any other queries? So what will our one important thing that we have to see here is, or we have to understand here is, how will the how will this particular you can say mm, how will the instruction or the CS and IP values get pushed into the stack? That is something very important that we can actually look for. Okay. So before that, we'll take one example also. Let me show that particular thing of how actually the uh, CS and IP value will be stored into the instruction pointer. The CS and IP value, first the IP value will be pushed into the stack. Okay. So first the IP value will be pushed into the stack, IP low, IPH, CS low, and CSH. Okay. One second. I just actually will take one example if possible. Uh, okay. Uh, Let me take an example here, which I can actually specify here. Just a second. Okay, never mind. So I was looking for a particular example from the textbook itself. Okay, never mind. One second. So let us put an example here itself. Yeah. Okay. So for an example of, let us say we can have an example this way for a call of direct. Okay. So call, let us say that 0003H. Okay. Uh, Again, or you can specify H. Yeah, that will be better. 0003H. So this will be IP low, IPH, and CS low, CSH. I can specify it directly as 0010H. Okay. So when I say this way, call 00H, 03H, 00H, 10H. So this will be IP low. This will be IP high, CS low, and CS high. Okay. So this will be then the new CS, okay, will be equal to 1000H, and new IP will be equal to 0300H. Okay. And let us say that the this particular instruction is here. Okay. The next instruction is, say, add AX comma BX. Let us say that. And this particular instruction is, let us say, is at location, okay, 0B45 colon H, okay, colon 1000H. Let us say that. Okay. Add is the next instruction. You have the main program here. Okay, you have the main program here, and the next instruction after call is this add, and add is present at 0B45 colon 1000H. That means this is the IP value, this is the CS value. So now let us say the stack pointer. Okay, the stack pointer, let us say, is at 2004H. H. Okay, so this is the stack. Okay, this is your stack, and this is 2004 H, SS colon 2004 H. It will have some value here. Okay, so when call instruction will be called here, or when will be invoked here, so what will happen is I will first push the IP. Okay, so I will first push the IP. So I will put 2002, 2003. Okay, so IP low, IPH. Okay, IP low, IPH. So it will decrement by 4. Okay, so first I'll put the IP low. IP low is what? Is 00. This is 10. Okay, and this is 2000. This is 2001. This is 2001. This is 2000. Okay, so CS high and CS low. Okay, so it will have your 0B here, and you will have 45H here. Okay, this is how the stack will be put, and the stack pointer will be here now. Okay, so the stack pointer will get decremented by 4. Okay, it will first push the IP and then push the CS, and then push the CS. For example, let us take one example, or I show the one example which was there in the textbook itself. Okay, so let us say that I hope you are able to see this. So this is one example which you have in your textbook, where you have a call instruction here. Okay, so your return location is 10,003H. Okay, that means your this is for a near call. Okay, this is for a near call. In this case, the IP value is 0003H. Okay, so your stack pointer before pushing was at this particular location, and now I will push 0003H into this. Okay, the most significant byte is 00. That will go into AFFEH. So that will have the most significant byte. AFFD is 03H in this case. Okay, because in this case the return IP value is 0003H. Okay, in this case, so the 03 will go into the lower address 03 here, and higher address will go into the higher. At the higher address, you will have the most significant byte. Okay, in the case of a far call, in the case of a, this is the effect of a, this is a near call. Okay, near read. In the case of a far call, okay, this is how your far call will look like. Let us say that call, okay, in this case 02000011. This is the example that he has taken. IP low, IP high, CS low, CS high. So it will go to 1100 colon. Okay, 1100 colon IP 0002. Okay, so that is what he went to. Okay, now the return address was 10,005. Okay, so if you split it, it will become 1000 colon 00 0005. Okay, so I will first, if you look at the stack, okay, stack will have the you'll first have the IP here. I think we have made some mistake here. Okay, so you'll have your stack was previously here. Okay, so this will be your IP. Okay, this will be your CS. Okay, so yeah, sorry, I think we made a mistake in the slide. So we'll push the CS first, and then you will push the IP. Okay, you'll first push the CS and then the IP. CS in this case was 1000. Okay, 1000 for the next instruction after the call instruction. Okay, so 1000 colon 0005. Okay, so first I will push the CS value. The higher byte of CS is 10, so that will go into the higher address. 00 is the next the lower LSB of the CS value, so that will go to the next address, which is the lower address. Okay, and then IP will be pushed. IP is 00 is the most significant byte, so that will be pushed, and then 0F 05. Okay, so we need to make a change here. Okay, so when I actually push it here, so my okay, I will decrement my okay. So in this case, your what will be pushed is first you will your CS will be pushed, and then your IP will be pushed. In this case, so CS high, CS low, IP high, and IP low. Okay, so in this case, it will be 0B45. Okay, so 0B will come here, 45 will come here, IP high is 10, and then 00. Okay, H of course is there. So this how you will get pushed. The particular thing will be pushed when you do a far call, right? Okay, any queries here? We'll end here. We will end here, but we will continue after the mid-semester exam, and we'll take the we will take some examples on these call procedures also.
Excuse me, sir.
Yes.
Sir, I was doing a previous paper. I had a doubt from there. The question
Before
was.
that, no, 1 second, please. I'll take it up once. Let us see if there are any other queries with respect to the instruction directly. Okay, any queries with that question we will take, but anything directly from the class? Mid-semester syllabus will have all the instructions that we have covered till now, except the call. Call we will not be able to have. Right. Any other queries? Right. Who was it who was asking from the previous question?
Yes, sir, it was me.
I don't know. I'm not able to see who is asking. What's your name?
Sir, my name is Mitesh Madan.
Mitesh. Okay. Yes, Mitesh. Go on.
Sir, the question was to write a logical equivalent instruction for subtract BL, BL, ignoring the flags.
Subtract BL, BL in ignoring the flags. If you do SUB BL, what will happen?
So it will become 0.
It will become 0. Okay, you have to write a logical instruction, right? Hello?
Yes, sir. Yes, sir.
What was the condition? You have to write a logical instruction
logical equivalent instruction
without
caring about the flags nature.
You don't have to care about the flags, right?
Yes, sir.
So you can just say and BL, 0.
So can we use here move BL, 0?
You should use a logical instruction, na?
Okay, okay. So
Move,
I thought
no.
I thought semantically equal instruction.
No. You should use a logical instruction, right?
Oh, okay. Thank you, sir.
Okay. Okay.
So,
Yes.
so this is Tushar. I also want to ask a question. Sir, in the data declaration of, let's suppose we have declared a label VCNT, can we move directly to the memory location, like move VCNT in brackets, BX?
Move VC. No, you can specify brackets. You need not specify brackets also. Now VCNT is what, a DW or a DB?
So let's say it's suitably declared. Let's say AX was 16 bit, so DW.
DW, you can do that. You can do that.
So I can straight away say move VCNT comma D comma AX, or in brackets I should say, or both are fine.
Both are fine. Both are right.
So because like I tried it on Massum, but it didn't work out. Like I was able to move straight away from VCNT to AX, but it didn't allowed me to move from a register to a this directly. So is it about Massum not correctly imitating the processor, or
Let's see that. One second. If you have time, we can look at that. If there is any query, you have a class right now, Tushar? You have a class right now? Look, Tushar, can you hear me? Tushar, can you hear me? Do you have a class right now? I don't know. Others, can you hear me?
Yes, sir.
Right. Okay, let's see
yes, sir.
that.
Sorry, sir. My
You
internet
have a
connection
class
was
right now,
not
Tushar?
stable. No, sir, no.
Then let's look
No.
at it. Okay, we'll have this dot model tiny dot data VCNT DB or DW some question mark. Okay, dot. I'll also have LOC1. Hariharan, you are also on the call, right?
Yes, sir.
Okay, so we'll look at your query also that you asked last class. Okay, dot code dot startup. Uh, Let us say move. Let's just put the move AX comma VCNT. Okay, it's not case sensitive, so it should not be an issue. Just say increment AX, okay, and then move VCNT comma AX and move LOC1 comma AH. Hariharan, I think your query will be solved if we execute this particular instruction. Move LOC1 comma AH.
Yes, sir. But I can't see your screen, sir.
You can't see my screen. Okay, I'm sorry for that. Right. Right. So we put it this way. 1 second. I have to stop sharing for a moment. I just compile that particular thing. DOS box is already there. Um,
Sir, you can stop recording if
yeah,
it's
yeah,
not
I can
recording.
stop recording here.